bottom. So you have true, true, false, and then you unpack true to its lambda calculus definition. You plug in true for x, but not true, false for y. So
right.
I don't see how you got that next step.
Oh, this one right here.
Yeah, what happened to oh, I don't know. You like that's just you plugging in true, so you drop the lambda, put in the
Right.
value of true.
So remember, I could pretend that there are parentheses there, or there really are. It's really that we're pretending there aren't. Because there you can just infer it from kind of how we write this. And that's exactly what I'm doing is I'm applying the true to x, and that's why the x, that lambda x drops off. It's because we've given that x, that lambda x, an argument, and we said, okay, well, x equals true. And so we've replaced all the x's in the term with true.
So what is the point of the trailing false, since it doesn't really seem to have any import in the program?
Yeah, in this situation, it doesn't. In the next example, it should.
Okay.
Okay, because here we did just the true, true case. Next, we're going to do one of the cases with a false in it. We should hopefully get false as a result. Okay, so we got, check mark there. That was the expected output. For and on true and true. So far, Arthur's idea is working. Yeah, and Arthur, I think that's probably a better way of thinking about it, is thinking about it as a single function with two inputs and one output. Probably better than kind of doing those as individual steps. And that's a good suggestion, is probably just fully apply everything. And that's typically what we do. But as we'll see in a second, it makes it harder to apply the formal rules. So that's why I kind of take that extra step, is formally, there's no rule for double application. But it is easier to just think of this as a function on two arguments, not as kind of the curried thing. So very, very good point there. So. Oh, and Arthur's got predictions for the other binary operations. So kudos for that. We'll play with those in a little bit. Let's keep testing this one though for now. Let's see if we get the correct input for something else. So let's do this time and on false and true. Let's do the same thing again, where we have, all we do is kind of sub in the definition for and to start with, and we'll start applying stuff. Let's do that first. Just kind of copy it down here, make it a little smaller maybe, and change the color. And this is applied to false and true. I'm going to give you guys a second to try and reduce these yourself. So try out some reductions here. And you're going to start by applying false and true to B and C. Okay, so subbing in false and true for B and C. So try that out yourselves and let me know when, what that first step should result in. Where all you've done is subbed in B and C. Ben, hold on to that for a second. We'll get back to that. I like what you're thinking, though. Does anyone have that first reduction? Whenever you do, throw it in chat for me. All we've done is a substitution. Okay, Linnea's got an answer for us. So Linnea is saying we should have false on true, true, false on false. Okay, I like that. Good first step, right? And we could look at that as being, you know, this was the B. And then the C gets subbed in for true. Or the other way around. True gets subbed in for C. How could we reduce this again? What's our next step? Can we finish this in one step? That's going to be my question for you. So we actually only need one more step. Maybe two if you write the definition of false out. Yeah, so we could also write false on do you mean false, true, true, or false, true, false? Omega. I think you mean false, true, false. So we could get true here, and that's because this true, it selects its first argument, which is true. So we could do that reduction. You don't even have to do this reduction. We could actually go straight to an answer because false, true, false is going to select the second argument, which is false. And that's a solution. So right on. Good work, everybody. So we're catching on to this. I like this. Now,
I'm not sure I followed that. So looking at your line where you have false, true, true, false, false.
Right? This line, right?
That line there, yeah.
Yeah.
I assume you're gonna unpack false as lambda x, lambda y, y.
Yeah, so let's do that.
Okay.
If I can get a good selection here. There we go. So we could unpack the false, right? Some folks are skipping that step now because we're starting to get comfortable, but that's okay. We don't have to. So we have lambda x, lambda y, y.
Right.
And then that's applied to true, true, false, and false.
Right. So would you not take your x and y as those last two false values?
Last two false values.
Hmm. So
You
like
mean these two?
all the way at your initial step,
Mm-hmm.
you took the last two values on the tail and plugged those things in sequential
Right.
order as B and C.
Right.
Here we have something similar, with the exception of the parentheses.
Right.
So why would you not take those last two, like all the way to the right?
Like
false, false?
these
Yeah,
two?
right. Yep.
Because of, right, you kind of answered your own question. It's because of the parentheses. So when we have parentheses, we group that together. So this is all one term, and this is all another term. So this would end up getting subbed in for y, or sorry, x. This would be y. Because we're not allowed to break this parenthesis off. That's kind of, it groups in, it's a single term for purposes of application.
Okay.
Does that make more sense? As soon as we're done with this example, we'll talk about the formal rules, and it should make it super clear why this is. So bear with me if it doesn't make sense. So now the way we reduced here, we could then reduce this x part. That's what we did in this step. So we kind of here, if we wanted this to be consistent, I ought to take this, duplicate it, and copy it down here. So here we've reduced the x part into true first. We didn't actually have to do that because it selects false, and we can kind of skip that step. So the nice thing about, nice or not nice thing, I guess, about the Lambda calculus is sometimes you can make smart decisions on what to reduce and what to not reduce. And this is one of those situations where we don't need to reduce x because this will select y. And maybe that wasn't, this will select y. So we can actually finish this all in one step. And we get false. So I want to take a step back to a comment that Ben made a second ago. So let's pull out our definition of and again. I'm going to actually copy what Ben said verbatim. So Ben says, I'm changing one thing about what he said. Couldn't we replace C true false with C? What do we think? Arthur immediately said that's actually smart. I feel dumb now. No, Arthur, I wouldn't be so hard on yourself because you did pull this definition up quick on your own, so you're doing okay. But can we do this? Basically, the question here, we could also phrase this question as C true false. Is it equivalent to C? What do we think? Yeah, so Arthur says yes. Because when C equals true, we get true. And when, I'll actually move this over. And when c equals false, the whole expression gives us false, right? And that's a pretty good signal that we can just draw this. Actually, it's not even a signal, that's an equivalence, right? We've hit every case. So this fact is certainly true. I'll turn it pink to kind of enshrine it, which means we can simplify our definition of and a little bit. So now our final version of and will be replacing that with B on C and false. And that is a final result. That is correct. And that's exactly what we have in the notes too. So good work, guys. Put a nice little QED box down there. Really good work. Good back and forth there. That's something else that's kind of cool about this, is that you can apply these equivalences and simplify your functions. It's a style of reasoning called equational reasoning. And that's actually what we've been doing with our reductions as well, is we've been figuring out kind of what evaluations are as equivalences. So let's take a step back and talk about our formal rules for this system. So good work on and. Definitely a tricky thing to get right. So good job kind of as a class coming to that answer, doing really good. But let's talk about the formal rules for the Lambda calculus. Oh, that doesn't work. Regerts. Okay. Just kidding. I tried to do something fancy. It didn't work. So I said there are 4 main rules, and then there's kind of a rule for reduction we also use. So I guess we could kind of say there's 5. But let's start talking about it. So the first rule we've actually already seen. We call this rule, and I'll draw us a table as we go over these. We call this rule substitution. Okay, and substitution just says basically when we can sub in a variable for something. That's this kind of square bracket notation we were using. So we say we will substitute E1 in for X in E2. So substitute expression E1 in place of X or sorry, a variable X in expression E2. Any questions about this rule? This is kind of a cheating rule because I haven't defined substitution in a really formal way. But we don't want to do that because it's actually kind of hard to do. So we're going to skip it. If you guys do want to know how that's defined, you can see the lecture notes. It's in, I believe, chapter 2 on page 12. They define it formally. And if we want to talk about it, I'm happy to next week. We can definitely dive into that. But this is kind of the only rule that's a little bit more hand wavy. But I think you guys understand how to substitute, hopefully. Just kind of wherever you see an X, put E1 there instead. in E2. Does that make sense to everybody? Questions about that? Cool. Sounds like we're good so far. Next, these are kind of the main rules now that we're getting to. This rule is called alpha conversion. And I'm actually going to change our colors here a little bit. Let's do these in blue. Yeah, we'll do it in blue. So alpha conversion says, and these are all rules for equivalence, basically. It says that lambda x dot e is equivalent under alpha. We kind of use a subscript a there, or subscript alpha, is equivalent to lambda y dot, and then anywhere where we sub in y in for x in E. We also call this renaming. Why do we call this renaming? So we call this renaming because if I had something like lambda x dot, let's say true x, right? Just some nonsense program. And I applied this rule, it allows me to rename, say, under y. And the variable names don't matter here, of course. I could have lambda y, where I sub in y for x in E. So here I have y in for x, in true xx, which is, of course, lambda y dot true y. Okay, so it's just renaming, but it's giving a formal way of doing that. This seems kind of like it's not useful, but take my word for it, it is in certain circumstances. You may want to do this. And there is one caveat to this rule, is provided y is not free in E. Okay, now you guys don't quite know what free means yet. We'll talk about that a little bit later, probably. But it basically says y isn't allowed to just already be an E, for instance. It's like E can't contain any y's if we do this. Otherwise, it would give y too much meaning inside of E. Everyone with me so far? Good example there. Let's get on to the next rule. This is the most important rule by a mile. It's not even close. This is called beta conversion. It's also called beta reduction. Sometimes just reduction. This is a really famous rule because it's actually what kind of gives the lambda calculus all its power. So here we have lambda x dot E2 E1 is equivalent to, under beta, E1 subbed in for X in E2. This is that substitution rule we were alluding to earlier. That's so important. An example of this say for lambda x dot x on y would be y subbed in for x in x, which then further reduces under substitution to just y. Questions about beta reduction? Are we still all with me? We've been quiet in chat for the last few minutes, so last 12 minutes. Hopefully everyone's with me. If not, you know where to type. And then the last one, this is called eta conversion. That's not how you draw an eta, though. That's an eta. And with eta conversion, we have lambda x dot e x. So e applied to x. So I could put parentheses there. Is equivalent under eta conversion to just e. And then the same caveat as before, provided x is not free in E. So provided E doesn't contain any x's inside it, right? All righty. That sums up the formal rules. So you guys will always be able to apply these 4 rules when doing reductions or doing equalities in this system. What you did before with this little fact right here, that was a beta reduction. Is you applied, wait, was it a beta reduction? It wasn't quite a beta reduction. Yep, I'm not going back there yet. It sort of was a beta reduction. You used a beta reduction there. What we've been doing, though, with all these examples, those are all, for the most part, beta reductions. You don't encounter eta reduction. You encounter eta reduction with some regularity, but not necessarily alpha conversions. Those don't happen a lot. We'll often call eta conversion simplifications. Yeah. And then I do want to make one more note, and I think this was the note that should clear up a lot for people. So we also have juxtaposition, which is a fancy word for stuff with spaces in it. So when we encounter something like E1, E2, E3, this groups E1, E2, and then E3, like so. I.e., expressions are left associative. Any questions? And I think earlier, this was the rule that was getting us hung up on those last two examples. So hopefully that clears that up. All righty. So if no questions there, let's go and try and define one more function today. And I actually think we will probably do a little bit with this still on Tuesday. Because I want to get to natural numbers and how we represent those, but we definitely don't have time today. So let's do the if function, or the if then else function. And in case you don't remember, this is the function kind of defined piecewise. It's defined like this. We have if true, and then in the notes they use u and w. We get u, and then if false, uw, we get w. You guys are probably getting used to this question by now, but how do we define this in the Lambda calculus? Where can we start per usual? So I'm going to write if, of course, equals question mark. What can we for sure fill that question mark in right now with? So Arthur thinks he has an answer. Arthur, you're leaving a little bit off of the front though. So Arthur is suggesting we put in lambda b dot b u w. What's wrong with that though? Specifically with regard to the u and w. Do we have u and w in scope right now? And also right now, this function looks like it only takes one argument. So how could we fix this? What could we do to clean this up? Any ideas? Nope, there Arthur. Arthur's got it. There we go. So instead, I'm going to cross this out. We have if is equal to lambda b dot lambda u dot lambda w dot b u w. All righty. Do we think this works? How could we test it? What could we do? There's only two cases to test, so we could test it pretty easily, I think. Let's test this by applying it. Let's do some examples. So let's do if true, and we'll leave the last two arguments as x and y. And we would expect this to be what? Probably x, the true case. So we could replace this with substitution as lambda b dot lambda u dot lambda w b u w on true x and y. And then we can sub all this in. True x and y subbed into there end up being just true x and y. And then true selects x, right? Correct behavior. Oh yeah, this is the correct definition, by the way, for those of you trying to write it down. Now we could do the same for false. So if false x, y, we get most of the same front matter. We get the same first reduction, except because that's just a substitution. So we have false here. And then in the next step, we sub in everything and get false x, y, which selects the second argument, which is y. So we get the correct expected behavior. Does anything seem fishy to anybody here? Oh, just that you take notes in pen. I'm sorry about that. The backtracking doesn't help. So I like the definition. It's correct. But let's take a look at something. I'm going to copy the definition here. And I want us to apply some of our formal rules here. So let's take a look at just kind of the inner part. Let's group this B and U together because we know we can do that through juxtaposition. And let's just take a look at this part I'm underlining right now. Can anyone apply a rule there? One of those formal rules we just took a look at? Take a look at those formal rules you wrote down. Can we apply any to this yellow section? Let's see if I can quickly copy the rules over. Can I apply alpha, beta, or eta reduction here? Micah thinks beta conversion maybe. Can't really do any beta conversion here, I don't think. So I'll give us a hint, or I'll just kind of tell us. We can do an eta conversion here. And why? So if I copy over lambda w dot bu w, I can do an eta conversion, right? I have the last argument and the lambda, they match each other. So then I can just get left with an e. So let's do that conversion. What do I end up with? I end up with just bu. Okay, and if I sub this into my if definition, I'm left with just bu. How about now? Can we do any other reductions here?
So can I ask you a question about your eta reduction there?
Please do. Yeah.
Okay, so we've got lambda x dot ex, right?
Yep.
And in the problem we have lambda w dot bu. So shouldn't you just get b back? If b would be equivalent, like b would stand in for your e, u would stand in for your x. You take u, plug it in for x, get back e, which would be b.
So here in this first step, all we're doing, and you might be getting a step ahead of me, we're making wx here. If we're kind of following the schematic, this would be our x. This is our e. And this is that other x, which lets me get e. Is that better?
Yeah, I think I get what you're saying there. Yeah.
Okay. If not, now's a perfect time to elaborate, but hopefully that makes sense.
Yeah, it just kind of seems a bit arbitrary to me how these parentheses get drawn.
Oh, okay. So remember, we always group, and that's that juxtaposition we were just talking about up here, is everything is left associative within expressions. So these aren't arbitrary, they're always there, these ones here. We just don't always write them. But in cases like this, they're quite important to remember they're there. So it's just left associativity. and maybe it's a practice thing too that just comes with working with it. Yeah, and then Arthur brings up an interesting point. So suddenly, we don't have a second argument, right? Or do we? So this is an interesting point. Does this behave in the same way? So let's try that out. So what if I did if, and I'm just going to copy the new definition down here, lambda b lambda u dot bu, and applied that to say, let's say true x and y. Not really sure why I put parentheses there. That wasn't important. Okay, so leave the y there, sub in true for b, and x for u. So now I have true x inside the parentheses and then a y on the outside. True is still expecting one argument. And so we can apply the y to true x, right? Or true x is still expecting one more argument. And that's why it still works. This partial application works here. And I'm going to skip ahead a little bit because we're right at time. So I'm going to kind of show you where this is going. Is from this point, trust me that this definition works. And if you don't believe me, try applying the rules yourself. And I promise it works. Or take a look at the course notes that I posted online. At this point, we have another potential reduction. I'm just going to kind of write it, and then you guys take a look later if you don't believe me. And I promise it works. Here we can do another eta reduction because we have lambda u and a u on the end with some expression e there. Okay, this fits the form again. So now under another eta reduction, we get lambda b dot b. Does anyone know what that's called? It's the identity. Okay, so at the end, with these reductions we've just done, we have the conditional is equivalent to the identity based off our definitions of true and false, which is kind of interesting. Now, why is that? We'll talk about that a little bit more on Tuesday. So we will pick this back up on Tuesday, I think, because I want to kind of bring that to a close. So there's an interesting reason for this. But I'll leave us there. Have a good weekend, all of you. Remember, midterm will be out sometime tomorrow morning. Due on Monday. Homework 5, I think it's 5, is out right now, due tomorrow. And homework 6 will go out over the weekend. And if you have questions for off stars, give me about 5 minutes, use restroom, get some beverage, and I'll be happy to hang out for a little while and answer office hour type questions. But otherwise, y'all have a good weekend, and we'll see you on Tuesday.